All right, so welcome back for section 6.2. This is going to be pretty quick because we basically covered all the major ideas in section 6.1. This is just going to be a section where we're going to talk specifically about normal distributions that aren't standard. The mean is not 0. The standard is not 1. Things are changing. Right? We are going to touch on something that used to be really, really important and isn't as important anymore, but sometimes we still do it, so we got to cover it. Okay, and that is that we can use a conversion to standardize any normal distribution. Okay, it's an idea that's slowly being phased out. It still has some relevance here and there. Okay, all right. So here's the idea. Suppose that someone gives you data about a distribution, a normal distribution, but it is not a standard normal distribution. And for whatever reason, you want to take x's and turn x's into z's, that you want to standardize it. Well, here's the formula. The formula says that any x can be turned into a z-score by taking x minus the mean for x's distribution and then dividing that difference by the standard deviation for x's distribution, where this guy right here and this guy right here are going to be the mean and the standard deviation of the x's. Right? Traditionally, when you do this, we round our z-scores to 2 places. This is a historic artifact. It's not really a rule, but it's done a lot. So basically what's happening here is, for some reason, someone handed you a non-standard normal distribution. Non-standard doesn't mean bad. It just means the mean is not 0. And you want to turn it into a standard. Well, you can do that with this formula right here. I will show you a problem work this way, and then we'll take a look at why and ask that question. Right? All right, so what proportion of men are taller than the 72-inch height requirement for shower heads? Okay, so I want to find the proportion of men who are taller than that 72 inches. And I'm told that the heights of men are normally distributed with a mean of that and a standard deviation of that. Right? So that means I'm looking at this problem where the mean is 68.6 inches. The standard deviation is 2.8 inches. Over here somewhere is 72 inches. And I want to find this right here. For whatever reason, I've decided that I'm not going to do this directly, and I want to turn this into a standard normal problem where my mean will be 0, my standard deviation will be 1, and I need to figure out what this x will become when I make it a z over here. So the first thing I'm going to do is I'm going to say that that z is going to be the x minus the mean divided by the standard deviation. I'm going to grab my calculator and go, what's 72 minus 68.6? There's my numerator. Divide that by 2.8. There's my denominator, and so I get a z-score of 1.21. So this becomes a z of 1.21, and then we want to find this area over here to the right of that. Okay. So then I'm going to grab my calculator, and I'm going to say, okay, distribution, normal CDF. My lower is that 1.21. My upper isn't listed, so I'll put in a big number. My mean is 0. My standard deviation is 1. And I get an area of 0.1131. So 0.1131, or to interpret that, about 11.31% of men won't fit under that standard shower head. Now, why wouldn't I have just done it directly over here? Why wouldn't I have just grabbed my calculator and said, just do this directly? Go to your distribution menu, go to normal CDF, put a lower limit in of 72, no upper limit, so put 1,000 in, put in your mean of 68.6, put in your standard deviation of 2.8, paste that back in. Wait a second, it's different. Why is it different? Did I type something wrong? Let me check it again. Distribution, normal CDF, lower limit 68.6, upper 2, paste it back in. I get 11.2. So over here, this is telling me it's 11.23%. Over there, I had 11.31%. Those numbers are different. Why? Well, the answer is right here. When I got that 1.21, I rounded. And when I rounded, it made my answer a little wrong. Now, this process, we used to have to do this every single time because the tables in the books are only z-scores. So we used to have to convert everything to a z-score to make these things work. Now, we don't need to do that. So this technique of converting everything over isn't really a good way to do things because every single time you're going to have to round right here. And when you round right there, you're going to get error. And so you're introducing error into your problem that doesn't need to be there. Now, if you click on the Help Me Solve This or Show Me an Example in the homework, because it's built around using the table for a lot of the problems, it's going to introduce that error, and you don't want that. So please don't use the table. Please don't use this conversion process. There are a rare few instances where this is still necessary. And when we get to those instances, we'll talk about them. But for us, if your job is to find area, find it directly. Don't convert to z-scores and then solve using those z-scores. It's just going to add extra steps. It's going to add places to make mistakes, and it's going to add error to your answers. Okay. Again, draw the graph. Some helpful values. Okay. So some helpful things here, some hints, draw the picture, right? Figure out, right? Don't confuse z-scores or x's with areas. Make sure you're doing the right graph, separating top 10%, bottom 10%, upper values, lower values, those sort of things. Draw the picture, right? If you ever get an answer that's bigger than 1 or smaller than 0, you know something's wrong because probabilities can't be negative. Draw the picture, make these problems work. All right, so here's an example. Disney World requires that people employed as a Mickey Mouse character must be between 56 and 62 inches tall. Find the percent of men that meet these height requirements. Right? Okay. I remember from before that men's heights are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. And I'm going to go back and check just to make sure. Yep, 68.6, 2.8. Okay. And I want to find out what percent of men could be Mickey Mouse at Disney World. 56 is way over here and 62 is over here. So we're looking at this piece right here, kind of. And I want to find that. There's my 58. There's my 62 for my min and my max, and I want to find that area right there. Now, I could convert 58 to a z-score. I could convert 62 to a z-score and do it that way, but no, I'm not going to. I'm just going to use technology to find it directly. I'm going to go to my distribution menu. I'm going to put in a lower limit of 58. I'm going to put in an upper limit of 62. My mean is 68.6. My standard deviation is 6.2. Run that command, and I get, 0.0091. So 0.91% of men. Now, two things are true at this point. One, my graph is terrible My sketch is horrible. There's no way that 0.91% is that giant yellow area that I drew there. But that doesn't really matter that my graph is bad. It's just I've got 58 left of middle. I've got 62 left of middle. I'm finding the right thing. But more importantly, what does this mean? Well, it means that less than 1%. So what does that mean about who's playing Mickey Mouse at Disney World? I'm going to bet it's probably not men. I'm betting that probably going to be women. A female Mickey Mouse. Okay. All right. After 1964, quarters were minted, so their weights had a mean of 5.767 grams and a standard deviation of 0.06 grams. If a vending machine determines counterfeit coins based on weight, what would the range of weight need to be so that less than 5% of valid coins are rejected? Okay, I'm going to think about this one for a second. All right, so there's an error in this problem, and it's my fault. I forgot to add in that the weights of the coins are normally distributed. So we're gonna work with that assumption. And so here's what I'm seeing. I'm hoping you're seeing the same thing. Coin weights normally distributed with a mean of 5.67 grams, a standard deviation of 0.06 grams. And I want to weigh my coins when they come through the machine and only reject coins that are too light, so they must be counterfeit, or too heavy, so they must be counterfeit. So I'm going to look for some number over here. I'm going to call that my x sub 1. And some number over here, I'm going to call that my x sub 2, that will reject coins. And I want to only reject about 5% of those. So I want those two tails to add up to 5%. Now, if I was speaking from a stats point of view, I could say that I am looking for critical values that are going to separate excessively light and excessively heavy, or significantly light and significantly heavy coins. And we could say then that this x sub 1 over here is z sub 0.2, I'm sorry, 0.025. But wait, no. Oh, negative, right. And this one is z of 0.025. Because when I write a critical value in this way, I am saying that the subscript number represents the area to the right. And when I put a negative on this guy, that means it's the area to the left. So that's essentially what we're finding here. We're finding critical values that are going to separate out significantly light and significantly heavy coins. Now, how I go about doing this? Well, let's see. Since I know the area and I want the x, I'm going to find those values. Now, one thing to note, these are not z-scores that we're finding here, right? Because we're not converting everything over to zeros and ones for means and standard deviations. But effectively, that's what we're looking for. We're looking for those values that are going to separate those things out. Okay? All right, so first we're going to find our x sub 1. I'm going to go to my calculator. Okay, I'm going to try something here. I'll be right back. All right, that's better. Set up two windows here. Since I'm using my calculator so much, might as well just leave it up. All right, so I'm going to find x sub 1. I'm going to use that inverse normal command. That left tail is that 0.025. My mean is 5.67. My standard deviation is 0.06. And I'm going to get that that's about 5.55 grams. And then I'm going to find my x sub 2 using the same command, that inverse normal. My area is 0.975. Now, where did 975 come from? Well, if I want this out here to be 2.5%, then everything to the left of it needs to be 97.5%. Paste that back in, and I get 5.79 grams. Okay, now how do I wrap this up and make it look pretty? Well, the last thing I want to do then is to say what that means, right? So we need to set the machine to accept from 5.55 grams to 5.79 grams, and then everything else will be either too light or too heavy, and will only be rejecting at most 5% of valid coins. All right, that brings us to the end of section 6.2. You'll see down there at the bottom of section 6.3. That's where we'll be starting next. Have a good one.